So we ended yesterday with expanding the sums, like when we had summation notation, writing out what that meant. This is the other way. When we have the expanded form and we want to go back to the sum from it. So, this would be my sum. Okay, I is the term number. So this would be term 1, 2, 3, 4, 5, and 6. So we're just going to add up from I equals 1 to 6. All right, well, this one is fairly straightforward because these are the numbers, 1, 2, 3, 4, 5, 6. So that would just be like we're adding up i's. But then they would all be positive. How did we see yesterday that we flipped between positives and negatives? Yeah, we had powers of -1. So I have to have -1 to some power times I to get this. All right, so if I do -1, let's say if I just did the I power, then the first term, -1 to the first would be negative. So that wouldn't work out. I need it to be positive. So let's see if I add 1 to it. So then when I put in a 1, I get -1 squared times 1, which does give us 1. When I put in a 2, I get -1 to the third times 2, which is -2. If I put in a 3, I get -1 to the fourth times 3, which is 3. So is this giving me the pattern we needed? Yeah. So the sum for this one would be from 1 to 6 of -1 to the I plus 1 power times I. Look at this one. I is the term number, so this is first term, second term, third term, fourth term, fifth term. So I'm adding up from I equals 1 to what? 1 to 5. All right, now I need a formula for that. So what do you notice all these have in common? Okay. So the bottom is the term squared. 5 squared, 4 squared, 3 squared, 2 squared. I could put 1 as 1 over 1. So all these are just 1 over I squared. And then if you weren't sure, you could check it. If you put in 1, you get 1. Put in 2, you get 1/4. 3 gives you 1/9, and so forth. So it does work. This one. So first, second, third, fourth, fifth, sixth, seventh, eighth, and ninth term. So I'm adding up from I equals 1 to 9. Okay, some of these have radicals and some don't. 1, though, isn't that the same thing as square root of 1? 2, isn't that the square root of 4? 2 radical 2 is the same thing as the square root of 8. 3 is the same thing as the square root of 9. So what's my pattern? The square root of I. All right. Any questions on those? So that's the few that we skipped, the 5 in the middle, what you're doing on those. And I will give you some time at the end of class to answer those. Now I want to get into, like, why is this even helpful? Why would I want to be able to write a summation formula? And it's actually true that there are shortcuts for adding some of these things up. So, our different summation rules. When we are adding up and we have a constant times the term that's changing, we kind of did this on our rectangles. All those were multiplied by the width, right? And the width was the same every time. So what did we do with that width? We took it out in the front and just multiplied it. So if they're all multiplied by the same constant, you can factor that out. If I'm adding up two terms, you can add them up separately. So I could add up the first one plus add up the second one. Okay, this formula, what that's saying is something like the sum from 1 to 3 of 2 plus I, let's say. So when you added that up, you would have like a 2 plus 1, a 2 plus 2, a 2 plus 3, right? How many times did this 2 in front get added? 3 times, because that's where we stopped. So if you're just adding up a constant, it's just that constant times the number of times you're adding it, plus the sum of the terms with the I in them that are changing. The last one tells me if I am just adding up sum from I equals 1 to n of 1, does that 1 have an I in it? No, so it's just the same thing over and over and over again. So what would that turn into? N. You're just adding 1 up n number of times, and so you get n when you do that. We're going to talk about some of the common formulas right now. A lot of times we just have I to the power. So it could be like first, second, third, fourth. That's just saying the thing that changes is your base. That's where the I is. And the exponent is constant. And we are going to look at formulas for adding up powers of 1, 2, and 3. So this formula for adding up powers of 1, you can put your pencils down if you want, you don't have to write this down, but just a little side note. If I said something like from 1 to 10, of I, we know it's 1 plus 2 plus 3 plus 4. Okay, and if you wanted to think about adding that up quickly, 10 plus 1 is 11. 9 plus 2 is 11. 3 plus 8 is 11. 4 plus 7 is 11. 5 plus 6 is 11. Right? So if we pair them, like highest and lowest, we can recognize that they're adding up to the same thing. So I had 11. How many times did I get a group of 11? 5. 5 groups of 11, right? Okay, so this would add up to 55. And you could do that if you're adding up from 1 to 100 or 1 to 200. Well, there's actually a pattern to it. If I'm adding up from 1 to n, okay, this number, the top was 10, and all my groups added up to 11. So if I'm adding up to n, all my groups are going to add up to n plus 1. All right, my number of groups was half of 10. So the number of groups would be n divided by 2. That's actually the formula for adding up powers of I. So it's n times n plus 1 divided by 2. So this is a shortcut that will allow us to add them up faster. Do you guys kind of understand where that formula came from? You could use similar reasoning to get the squares, but it's a little more complicated. Are you guys okay if I just tell you what the formula turns out to be? Okay, it starts out the same. It's n times n plus 1 times 2n plus 1 divided by 6. And the last one we're going to do is I cubed, which is just your I formula squared. So it's n squared, n plus 1 squared over 4. You do need to know these formulas. So you might highlight it, put a big star next to it. There's 3, so only 3 we're going to memorize, but they will be very useful for us for evaluating summations. So I want to show you a couple examples of how that is used. If I wanted to find the sum of the first 13 positive integers. Okay, so I'm adding up from 1 to 13, my i's, my powers by. So I could certainly write out 1 times 13 divided by, or 1 plus 2 plus 3 all the way up to 13. Or we can use our formula. The formula for powers of I is n, what's my n here? 13 times n plus 1, so 13 plus 1 is 14, divided by 2. And that gives us 91. Okay, check it. Add up 1 through 13 on your calculator. Everybody grab a calculator and add it up. Nobody's exempt. You guys all have to participate.
Oh. Years,
So were we right? Yep, so it worked. All right. B, I want to add up the first 13 squares. So from 1 to 13 of I squared. So the I squared formula is n, which is still 13, n plus 1, which is 14, 2n plus 1. So 2 times 13 is 26, plus 1 is 27. And what do we divide by on this one? 6. So the first 13 perfect squares add up to 819. And we can check that. We can do 1 squared plus 2 squared plus 3 squared plus 4 squared all the way up to 13 squared. C, if I want to add up the perfect cubes, that's n squared times n plus 1 squared over 4. That gives me 8,281. So definitely faster than just constantly plugging in the numbers on our calculator. Also, a little more accurate. When you're pushing a lot of buttons on the calculator, you're more likely to make a mistake, right? So this could save us a lot of time, especially if I said I want you to add up 1 through 1,000. You don't want to sit here all day pushing those buttons on the calculator, but we can use this formula to quickly evaluate it. All right, let's practice some more of these. So if I want the sum from 1 to 20 of 7i squared minus 5i, we have to use our rules of summations a little bit. So summations tell me if I have things added up, I can add each of these separately. Bryson?
Yeah.
It also told me, what can we do with these constants in front? We can bring them in front of the sum. So it's 7 times the sum from 1 to 20 of I squared minus 5 times the sum from 1 to 20 of I. Okay. And then we have formulas for adding up I squared and I. What's the I squared formula? Okay, my n is 20. N plus 1 would be 21. 2n is 40, plus 1 would be 41. Divided by 6. And then our I formula is n times n plus 1 over 2. So now we can use our calculator to evaluate this. We're at 19,040. So definitely faster than writing out 20 terms with that whole expression. I want you guys to try the next 2 examples. We did real well on these. So the first one, we're adding up from j equals 1 to 8. I'm adding 5. Can I go ahead and write it as 2 times the sum from j equals 1 to 8 of j? Okay, so this says I'm adding 8 up 5 times. So you could, if you wanted, if you factor out that, take out the 5, all you're left with is a 1. What happens if I add up 1 8 times? We just get 8 times the 5. Okay, so you could either think of it as 5 times 8 ones added up, or you're actually adding the number 5 8 times. So if it's a constant, you just take your constant times n. Minus 2 times, if I'm adding up j to the first, my formula is n times n plus 1 over 2. My n is 8, n plus 1 would be 9, over 2. So that gives me 40 minus 72. So we get negative 32. So make sure you're not dropping that 2 and the 5, those constants that we have there. Does that make sense? What about the back row? You have to answer me.
I got the. What's the 8 times 9 divided by 2?
That's the formula that we said if you're adding up powers of I.
Oh, okay.
So as long as it's starting at 1, the number on the top is just your n. So n was 8. 8 plus 1 is 9, divided by 2. Other questions?
So it does not have to have an I, or in this case a J, so to be split apart.
Right. It's on, like, if things are added or subtracted, you can break them apart and do the sum of each term. So let's look at this one. If I'm going to write this, how many sums would I have? 3. So we have the sum from I equals 1 to 5 of I cubed minus the sum from 1 to 5 of 3i. So I'm just going to pull the 3 out in front. plus the sum from 1 to 5 of 2. Alright, so if I'm adding up I cubed, look at those 3 formulas I told you we had to know. The I cubed formula is n squared, n plus 1 squared over 4. N is 5, so we have 5 squared times 6 squared over 4. Minus 3 times the I formula. So the I formula that we wrote down was n times n plus 1 over 2. So my n is 5. So 5 times 6 divided by 2. Plus, if I add 2 up 5 times, that's 2 plus 2 plus 2 plus 2 plus 2. So I end up with just 2 times 5. So if it's just a constant, you can just take it times n. So if I add all this up, help if I push the right buttons on my calculator. We should get 190. Do we have questions on that? Let's look at the next one. Okay, we do not have rules that allow us to bring sum inside a parenthesis with exponents. So what do you think I should do with the 2 plus 1 squared? FOIL it. Here we go. 4k squared minus 4k plus 1. So then my sum formula. I can do the sum of each, pulling out the coefficients. So 4 times the sum from 1 to 7 of k squared minus 4 times the sum from 1 to 7 of k plus the sum from 1 to 7 of 1. Alright, k squared formula is n times n plus 1 times 2n plus 1 over 6. What's my n? 7. So we have 7. 7 plus 1 is 8. 2 times 7 plus 1 is 15. Or 6. Minus 4 times the k formula, which is n times n plus 1 over 2. So 7 times 8 over 2. Plus, what happens if you add 1 up 7 times? You get 7. Just 1 times 7. All right, so now we evaluate. Any questions on that? Okay. Let's stop here for now. So you need to finish the handout from yesterday. And I'm going to give you a new handout. I still need to go over the very last question. Yesterday's lesson took me a little bit longer, so I'm a little bit off, but I'll get caught back up Monday. So you're only doing, it's only 6 questions. You're only going to do 1 through 5 on the handout I'm giving you today.